All right, as we get started, let's go and review some terms we've been talking about recently. Obviously, had a quiz in our last lesson over a lot of this, but we're studying motion. And what do we call the study of motion? Audrey? Mechanics. And of course, we're specifically looking at kinematics, right, at this point, not really concerned with what's causing the motion, just the motion itself. And we said that as an object moves, it moves at a certain rate or a certain speed, but we generally concern ourselves more with not speed, but speed in a particular direction, which is velocity. Good. And velocity's direction, again, can be hard to define if the object is constantly changing course, but we take care of all of that. And we make it a perfect world scenario by only concerning ourselves with straight line distance from point A to point B, which we call displacement, which also allows us to define the direction then. And 5 key equations that you need to know. But the first one is this equation for velocity. What is that equation? Audrey? Good. Average velocity is displacement per unit time. And we said generally velocity is going to be in what units, class? Meters per second normally. We could also go US and use feet per second, or if we're talking, traveling and such, here in the US we use miles per hour. So any of those would work, generally meters per second though. But we said that as an object is traveling, this is an average velocity because of course the velocity can change. And if an object does change velocity, we call that change in velocity per unit time. Kendall? Acceleration. Okay, so acceleration, that change in velocity per unit time. In equation form, back to Kendall for redemption, what's our equation for acceleration?
A equals v sub f minus v sub I over t.
There we go. So the change in the velocity over time, of course. Can acceleration be negative, class? Yeah, acceleration can be negative. What does that mean if acceleration is negative, Audrey? Well, we call it deceleration, but practically speaking, deceleration is simply, plain English, slowing down, right? So it just means you're slowing down. What about velocity? Can velocity be negative? It can be if you've predetermined, for instance, we said yesterday, right? If I'm walking to Audrey's desk, if we've predetermined that's positive, then any motion away from Audrey's desk could be considered negative, right? So negative just means going back or going in the opposite direction. Not necessarily even walking backwards or going backwards, but going in the opposite direction. We had 3 other key equations for this chapter. One of them kind of was just a common sense way to look at average velocity. Not so much even a definition of velocity, like displacement over time, more a definition of what average means. Kendall? How else could I find an average velocity, particularly for an object that did accelerate, so where there was an initial velocity and a final velocity? Help, Audrey? Find average. How do we average things? Add and divide by 2, right? Okay, so if there's an initial velocity and a final velocity, add them and divide by 2. Or we could say take half. Not a problem to say divide by 2. But there's our next equation. It's just the definition of what average means. This assumes uniform acceleration. May or may not actually have it. We're going to assume it anyway. Then there were 2 other equations that were a little bit longer and a little bit weirder and a little harder to memorize. Do you remember either of them without looking? So we did not study the equations last night, apparently. One of these you should have used in both homework problems. So glancing down at our homework, Michael.
VI squared. I'd use 2 different equations. So equals VF squared minus 280.
Okay, that's not the way I had you memorize it, but it's not wrong. I had you memorize VF squared equals VI squared plus 280. But if you move the 280 over, you have what you said. VI squared equals VF squared minus 280. So here's an equation that uses initial and final velocity along with acceleration and displacement. Then there's another one we used a couple times yesterday. It was a rather lengthy equation or formula for displacement. Do you remember that one? Okay, Audrey, read it for us out of your book there.
D equals VIT.
All right, of course you will have these memorized soon. Say by Friday, you'll have these memorized, yes? And we'll practice with them today as well. Just looked at them yesterday briefly. Page 93, look at problem number 8. Read that for us if you would, Kendall.
A car left skid marks 16 meters long when the driver brought it to a quick stop as he was traveling east. Assuming the brakes decelerated the car at negative 15 meters per second squared, how fast was the car traveling when its brakes were first applied?
All right, so this is kind of a little bit, I guess, what police officers would use. If a guy lays on the brakes, of course, brakes lock up, car slides along anyway despite the friction, leaves the skid marks. I've got some skid marks in the street near my house. It's still really, really thick rubber that's still left there. And anyway, the skid marks show, okay, from the time the brakes were slammed onto to the time the car finally actually stopped because of its own momentum, what was its deceleration, or how fast was the car traveling at the moment it slams on the brakes. So the 16-meter long skid marks, what would that be, class? The distance, the displacement rather, right? Assuming it's kind of traveling in a straight line. Once you lay on the brakes, that's kind of what happens, right? Kind of lose, especially without anti-lock brakes. Lock up, 16-meter long skid marks. That's the displacement that the car travels from time the driver slams on brakes to avoid hitting whatever. And it doesn't say what he was trying to avoid hitting. It just, he came to a quick stop. We know if he did come to a stop, class, we know that the driver's final velocity was 0 meters per second. We also know that this particular model of car, based on its mass, based on other factors, we know that this car, if you jam on the brakes, will decelerate at negative 15 meters per second squared. Okay? So all different cars are different, but this particular one, it says decelerates, but deceleration is just negative acceleration. So we're going to represent A here, and it is good. Now again, they gave you the negative. Don't count on always getting the negative, right? But if it's deceleration, we know it is negative. And the question was, how fast was the car traveling? We're finding the initial velocity. Basically finding out, was he speeding? Okay, is he at fault? If he was speeding, he's at fault. If he wasn't speeding, then whoever got out in front of him was probably at fault. And then police officers can determine, at fault. And insurance companies like to know that. Any of you been in an accident yet? Hopefully not. That's always good. Audrey's not saying no. Anyway, my wife and I guess my wife's been in 2, and then the third one with me. I was in 1 with her, and then she's been in 2 by herself just in Chloe's lifetime. So last 7 years, I guess. And so anyway, none involving skid marks though. All right, we're not that fast. So the point is, you're going to look, remember, for an equation that has these 4 things in it. And Michael already identified, it's this one. Michael also realized because he wanted the VI by itself, he was going to ditch the 2AD as a negative. So he said V sub I squared equals V sub F squared minus 2AD. How many have that equation? Or this equation that you kind of rearranged? Now, the nice thing is, since the final velocity is 0 anyway, class, just cross it out. Yeah, let's move on with life. But do realize it is a V sub I squared. So if I just want V sub I, I'm going to have to take the square root. So if your car was going really fast, probably you forgot to take the square root. All right, so you can always entertain a little idea of realism with your answers here. So we've got a negative 2 times the acceleration, class, which we said was negative 15. And then your displacement was the 16 meters. Notice we have negative times negative gives us a positive, which is important, because if it came out negative, can you take the square root of a negative, class? No. We can't have imaginary initial velocities here, okay? So it's an important thing that the negative signs work out there. Multiply, take the square root, that's what, 480, take the square root, getting somewhere in the neighborhood of 21.8, something like that. What's the actual number you got when you worked it out? 21.9 rounded? 21.90, blah, blah, blah. Okay, because rounded to sig figs, we're only allowed 2 sig figs. So we're going to say our answer is approximately 22 meters per second. How many had the 22 meters per second? Question, Kendall. Makes sense? And what did you have for your answer?
I had a really big number.
Was it the 480 something?
Yes.
And you just forgot to take the square root. Okay.
Yes.
Audrey?
I have no idea.
No idea what you did. Did you write a formula?
I wrote out a list, but I didn't actually write out a formula.
Okay, yeah, so the point of the list, so you wrote out this list you said. Okay, the point of the list is to help you pick the formula, then write the formula. I manipulate the formula and plug in the numbers. Just keeping the work nice and neat so you can see everything that you're doing. Does it make sense now? Questions at all on this one? Look at number 9, and go to read number 9. Oh, here we go. This goes back to what we were talking about yesterday with driving guidance. Read number 9 for us, Michael.
A car is capable of accelerating at a rate of 3.2 meters per second squared. If it is going 11 meters per second when it leaves the curved portion of the entrance ramp to an expressway, how much straightaway does it need to obtain 35 meters per second before merging with the traffic?
As we said yesterday, notice that's before merging with traffic. Get up to the 35 meters per second before merging with traffic. But we beat that horse yesterday. And we were all in agreement there. So we just write down the numbers. The first number I see here, class, is the acceleration. 3.20 meters per second squared. Says it's going 11 meters per second. That's my initial velocity is the 11.0 meters per second because it says it's going to obtain 35 meters per second. Final velocity. And the question asks, how much straightaway does it need? And this again is kind of where we go back to that first exit. I know, Audrey, y'all live in Phoenix City, so you are forever taking that, River Road to the connector to the highway, and it's that long curve where you can't go super fast, and then as soon as it hits that straightaway, you really do have to hit it pretty hard because you don't have much straightaway there. This car, how much straightaway does it need? Plus, it's asking for the displacement, not the time, but it's asking for the displacement needed to get up to speed. Well, once you've made your list, you pick out an equation that you want to use. Which equation do we want to use here, Audrey? The same one, right? The v sub, say it with me, class, it'll help us memorize. V sub f squared equals v sub I squared plus 2ad. But, Audrey, since we're solving for the d, we want to maneuver things a little bit here. Tell me what to do to get the d by itself.
Subtract the v squared and divide by 2a.
And there we go. So we're going to square the v sub f, square the v sub I, subtract, divide by 2a. So when we square the 35, what do we get? 1225, and then we're going to subtract the 11 squared. Shouldn't need a calculator for that one. 121, and then we're going to divide it all by 2 times a. We could probably do that in our head. What is twice the acceleration here, class? 6.4. So we'll subtract the 121 from the 1225 to get 1104. Divide that by 6.4. And how much straightaway do we need, Audrey?
172.5.
Comes out evenly? All right. How many sig figs, class? 3 sig figs. So we're going to say approximately, Audrey. And displacement would be measured in meters. There we go. How many had 173 meters for this one? Okay, Michael, good to go on both of them then. Questions, ladies? All right, did you use this equation, Kendall?
Mm-hmm.
What was your answer?
I actually know what I did. I didn't set it up right, like getting the d by itself. I'm divided first before moving.
Oh, you try to divide away the 2a
Yes.
first. So get rid of the least attached
Yeah.
thing, right? Going all the way back to algebra class. Get rid of those worthless plastic donuts before you take the baby blanket. Okay. All right. Good. Another question. You weren't in my algebra 1 class. It's okay. It's okay. She knows what I'm talking about. She knows. All right. Questions on this? All right. Now, there's another way you could solve both of these. I just want to look at this one though. What if instead of finding the displacement first, what if you said, well, I want to see how much time it's going to take, and I'm going to use time to get displacement. You could do that. How would I find the time needed to get up to 35 meters a second? Car can only accelerate at 3.2 meters per second squared. That's its acceleration rate. Okay, maybe, I don't know if that's fast or not actually. Let's say it's not. Maybe that's Michael's SUV. And there's a whole lot of mass to be pulling here. And so, it's old. And we're speaking of old, Audrey's car, right? Acceleration ain't what she used to be, And so this is just what we got. How long is it going to take? How much time is it going to take to get up to that speed? What equation could we use if we wanted to find time, Kendall?
d equals v sub I times t plus 1/2 t squared.
Well, then I'm solving for time and there's a quadratic with the time. Ugh, I really hate that equation unless I already know the time. I don't mind plugging in the time, but I hate solving that one for time. That just factoring and all kind of whatnot. I'm lazy.
The acceleration.
Yeah, the acceleration equation, because if I use this to get the time by itself, all I gotta do is alternate. This is actually pretty easy to do, right? Just alternate. So if I were to take the final minus initial, you can get this in your head class, what's the final minus initial? 24, and divide that by the acceleration, which is alternated down here, 3.2. How much time does it take to get up to speed? 7.5 exactly? So if we know the time is 7.5 seconds, now what I could do is I could use this equation to find displacement. Because I know the initial is 11 times the time of 7.5, half the acceleration times the 7.5 squared. It's a little more obnoxious, but I could, right? What is 7.5 squared? Find it.
56.25.
Keep that on the calculator. What's half of 3.2? We can do that in our heads. 1.6. So take what's on the calculator times 1.6. What do we got?
190.
90 even? Okay. Now take 11 times 7.5. Call it.
82.5.
And add that to the 90, and notice what we get. Same 172.5. Now, I think this way is definitely more direct. But I mean, if you wanted to go that route, or even if we wanted to go this route, how can I get the displacement by itself in this equation, Michael?
Multiply the t.
Yeah, just multiply the t. Now, to get this, you have to average the velocity. Average means you do what, class?
Add by 2.
Add in half, add and divide by 2 for these two things. So add to get 46, so what's that divided by 2? Okay, so if the average velocity is 23, multiply the average velocity by the time of 7.5, and what do we get? 172.5. The point is there's a lot of ways to get it. The goal, though, is to find the easiest equation, and the easiest equation was this one here, right? So we want to do it the easy way. You could do it all kinds of different ways, but definitely the easy way is our preferred route. Questions on the homework? All right, look at page 88 now, if you would, please. Turn back to page 88 and read example 6.7, if you would. Audrey. Try 89, example 6.7.
How far will a bird fly if it accelerates at 2.4 meters per second squared from an initial velocity of 6 meters per second to a final velocity of 18 meters per second?
Okay, not sure how they got all those readings, but whatever. I guess radar gun gets the velocities. Getting the acceleration is pretty cool. All right, anyway, ours is not to question, ours but to plug in numbers. All right, so what's the first thing I'm going to write down here, class? Well, I'm not ready to pick an equation yet, right? Acceleration is?
2.4.
Meters per second squared.
You can do this with me there at your seats. Let's see, the next number I should write down.
Initial velocity.
Initial velocity is?
6.0 meters.
All right, then I write down
Final velocity
is?
18.
And I'm looking for the displacement during the acceleration, by the way. This isn't the entire flight of the bird. It's just the displacement during this acceleration of the bird. All right? And maybe it's y'all ever seen like the little mockingbirds attacking the crow or the hawk or whatever? Those mockingbirds are vicious. I've seen them attack cats before. And so, or even the little sparrows sometimes, they'll go after the hawk if the hawk is too close to the nest or whatever. So maybe the hawk's just sort of lazily circling or whatever at 6, and all of a sudden a little mockingbird comes pecking at its tail. So it speeds up. Well, during the speed up time, till it gets up to speed, how far is it going? That's the question. Which of our equations, you can either look at the bulletin board or looking in your notes, which equation should we probably use for this problem? Kendall?
V sub f squared equals vi squared plus 2a.
There we go. The one we used the last couple times, actually, right? And you'll memorize it because you'll use it so often. But yeah, so we are solving once again, kind of like we did for the last problem class, solving for the displacement. Okay, Kendall, here we go. You said you messed it up in the homework. You're going to get it right this time. What do we get for the d by itself?
V sub f squared minus v sub I squared over 2a equals d.
There we go. We're just going to plug in the numbers. So we're going to square the 18. Oh, we could do that in our heads if we remembered it from last year. Or we can plug it in the calculator. Wishful thinking. 324 minus, surely we can do 6 squared.
36.
Okay, there we go. We got that one at least, okay? And what is that when we subtract?
288.
Say it again?
288.
288. And we're going to divide that by 2 times a. You could divide by 2 and then also divide by the a, but I think it's easy enough to double this acceleration in our heads.
4.8.
So we divide by the 4.8, and how far does Birdie fly during acceleration?
60 meters.
Comes out evenly?
Yes.
Wow. So 60 meters, need how many sig figs? 2, I believe, right? Yeah, go 2 sig figs, so
Point.
60 point meters. There we go. And I believe that's the answer then that they had there. Yes, and it is. Questions on that? Example 6.8 is an interesting one because this one involves a little bit more. How many of you, as you're driving, you've learned that if you look at the lights for the cross traffic, if you see it go yellow and then you see it go red, you know your light's about to turn green. How many have noticed that? Or maybe you've noticed like a crosswalk, the little orange hand is flashing, and you notice when it goes steady, you have like 2 seconds and then your light turns green. Okay? Have any of you ever tried to like 1/1000 right as it's turning green as opposed to it turns green and then I react? Any of you ever done that? Or maybe you're driving up to it and you're kind of coasting and you're watching and you're calculating and you're like, I don't want to have to actually stop and lose all my momentum because gas prices, right? We're just trying to be economical, good stewards of the environment. That's what it is. And so we kind of time it right. I did that one time. There's a traffic light on River Road that I had down to a science. I thought, somebody changed the timing and it is no longer 2 seconds after red for the cross. It's 3. Well, so one of the ladies in our church, whose husband is a police officer, was sitting at the light, and I'm coming up in the right lane. I'm gauging. All right, just went red. 1/1000, 2/1000. It was still bright red. 1 second later, it turns green, and she's looking at me like, mm-hmm. So anyway, they moved away to Atlanta now, so I'm good. But it's your aunt. So anyway. That's kind of what we got going on here. Example 6.8, go ahead and read it for us, Michael.
A truck passes a stopped car at an intersection just as the traffic light turns green. The truck is traveling with a constant velocity of 15.6 meters per second. The car begins to accelerate at 3.4 meters per second squared just as the light turns green. How much time will it take for the car to overtake the truck? How far will the car travel in that time? And find the car's velocity when it overtakes the truck.
All right, so Audrey's sitting there in her little Saturn, and Michael is driving up in the truck, and Michael's got this thing timed to a science. He doesn't even hesitate. He has extreme confidence in his calculations. He never even slows down, just a constant 15.6 right past Audrey. And Audrey's, but if she just keeps at it, the little engine that can will, and she'll eventually catch up to Michael if she just keeps speeding up, right? That's what we've got going. Car sitting still, truck, and the car starts to speed up, and eventually car will catch truck if car continues to get faster. Now, car may be speeding at that point, okay? We don't advocate speeding here at Grace Christian School, for the record. I don't necessarily advocate gambling with traffic lights, even though I do it. And anyway, so 2 things here. Here's the car, and here's the truck. And truck, and the car, and eventually, right here, they're next to each other as Michael waves as he drives by. And then here, for a brief split second before Audrey now blows by him, okay, and that's before she gets pulled over, she waves at Michael. And during this time, they will have traveled the same length of time, and they will have also traveled the exact same displacement, correct? So the times of travel will be the same, and the displacements will be the same. So I'm going to separate these two things into two columns. We'll have car and we'll have truck. Now technically it's an SUV, but whatever. Okay, so let's start with the car. The car was sitting at the stoplight. So
initial velocity 0.
Initial velocity 0, okay? At this moment in time, do we know how fast the car is going? No. That's actually one of the things I believe we'll find. It was part, which part of the problem was that?
C.
Part C, right? Find the car's velocity when it overtakes the truck. So in part C, we're going to find this. All right, what else do I know about the car? Well, I know that the car's acceleration is
3.4 meters per second squared.
I don't know if that's good or bad. I don't know. So maybe we'll say it's really good and Audrey's car is more souped up than we thought it was. All right, she's done some work on her car. We don't know the time and we don't know the distance. Well, that's all 5 things, right? I mean, as you look at your equations, that's it. We don't know a whole lot. I do know that the time will be the same for both. I know the displacement will be the same for both. So I'm going to set this aside. Which equation has these 4 things in it? Which equation has these 4 things in it? Audrey? VI, A, T, and D, all at the same time. Since we're saving that final velocity for the last part. Which equation page? Well, the only problem is to average a velocity, I need to know what the final was. So no, and I want something that's going to use the displacement in it too. And that didn't have displacement in it. Might be staring at her and she's just missing it. That happens sometimes. Kendall?
D equals V sub I t plus 1/2 a t squared.
There we go. So this is the equation we're going to shoot for. But notice, since the initial velocity is 0, class,
0 t.
the V sub I t is just going to become a 0 itself. So we can say that the displacement of the car is 1/2 a t squared. So far, so good? Now let's go to the truck. The truck was already going how fast, class? 15.6. And that, according to the problem, that velocity does not change. It's just a constant 15.6. We could say that initial and final are both 15.6, but the better way to say it is that the average velocity is 15.6 meters per second. We don't know the time, but we do know it's the same as this time, and we don't know the distance, but we know it's the same as this distance. The acceleration would be 0. I don't really need that. So I need an equation that has those variables in it. Let's go back to Audrey. Which equation has these variables in it? Yeah, V sub AV equals D over T. But here's what we're going to do. What relates these two things together is that both the displacements and the time are the same. I'm going to lock in on the fact that the displacements are the same. You could go either route, but it's going to be easier with displacements. Since the displacements are the same, if I could rewrite this for displacement, I could set this displacement equal to that one. Does that make sense? How would I rearrange this to get displacement by itself, Michael?
D equals VAV times T.
Yeah, displacement is average velocity times time. So if I take the acceleration of the car, half of that times time squared, that's got to equal the average velocity of the truck times time. Make sense? So that's what they did in the sample problem. They took the 1/2 of Audrey's acceleration, times time squared, which we don't know, and set it equal to the average velocity times the time, which I don't know. And now we have a single equation with a single variable in it. Now we can solve. However, remember, Kendall, I said I don't like solving for time using this equation because it makes it quadratic? There really isn't another way to go about it. Other than getting time by itself, in which case now you've got a square root, and that's even worse. You've got a radical. It is a quadratic equation. Let's simplify it a little bit. And as we're used to doing from algebra class, we set quadratic equations equal to 0. All right, so all those things we learned from algebra coming back. Let's start by just cutting the 3.4 in half, though. T squared. And then let's set it equal to 0 by bringing this over as a negative 15.6t. Once you set a quadratic equal to 0, then I mentioned this a second ago when I was complaining about why we don't want to use this for solving for time. Because you get a quadratic and then you have to factor. Ooh, you're not allowed to forget anything. Set them equal to 0 and factor. Now, how would I factor this? It's not a trinomial, so I can't backwards FOIL, but I can at least pull out a t. And if I pull out the t, it's going to leave me with. So remember the keys to quadratic equations. A little algebra review here is set it equal to 0, factor, set each factor equal to 0. So we're going to say that time is 0, and 1.7t minus 15.6 is 0. Now obviously when it says time is 0, that means that they are equal right here, right at the start of the race, so to speak, right? But I'm interested in the time up here, and that's going to come from solving this little guy. So at your seats, add and divide, and what is the time it takes for Audrey to catch up to Michael?
9.176 blah
Blah, 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 9.176, blah, blah, blah. Put that in the memory of your calculators. And 9.176, blah, 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 9.176, blah, blah, blah. It's going to be the same for both. That was one of their questions, right? Letter A was how much time will it take? So letter A, let's round it off to how many sig figs? 2 sig figs. So we're going to say 9.2 seconds. There's our answer for letter A. Letter B asks kind of what we've been wondering all along. How far will the car travel? What will be the displacement? Well, now that you know t, I can now solve either saying d equals a half at squared. Well, that's Audrey's, right? Let's do that. Let's take a half 3.4 times memory squared. A half of 3.4 times memory squared. What was Audrey's distance? Okay, now let's do the same for Michael, except for Michael, his equation was average velocity times time. Take the 15.6 times the memory value. You got a different number? What do you get for 15.6 times the memory? Call it?
143.
143.15, blah, blah, blah. Let's go back over here. So I got my memory, and I'm going to take 0.5 times 3.4 times recall 1 squared. Now I'm getting 143.15 over here, not 153, unless I just heard you guys wrong. Either way, right, no matter which equation you solve, as long as you do it right, you should get the same distance, because again, they're traveling the same distance. So 2 sig figs, class. 140 meters down the road. They're getting 140 meters down the road, and Audrey races past Michael. 9.2 seconds have elapsed. Part C, she's speeding, at least we think she is. How fast is she going when she finally catches him? All right, so I would put this 143.15 in memory too. Now we need to know Audrey's final velocity. And all options are on the table, right? I've got everything I could possibly need. Which equation, and you've got all the variables here, which equation do you want to use that involves a final velocity, Kendall?
V sub f squared equals V sub I squared plus 2.
I think it's a great choice because the V sub I is 0 anyway, class, so
2.
Cross it out. Don't forget, we have to do what, class?
Take the square root.
Take the square root. So at your seats, we have the displacement in the memory. We know the acceleration times 2, and then take the square root of that. How fast is Audrey going when she catches up?
31.2 meters per second squared.
31.2, we'll round, or careful, 31 meters per second, right? Because it's just velocity. So now, again, I'm kind of picturing, I mean, you're coming off a traffic light. So that means you're in town, and she's going about 65 miles an hour. Yeah, definitely busted for speeding. All right? You're familiar with Reynolds, right? Okay, yeah, I am too now. So my sister lived in the Macon area, so to get from here to there, you go through Reynolds. And so, you know, the speed limit is like 65 miles an hour almost the entire way. Except at Butler, you have to slow down, and through Geneva, you have to slow down, and that's like population 52 people. And in Reynolds, you have to slow down. And y'all know how it is when you're approaching a red light. You slow down, slow down, slow down. And then when you see the light turn green, what do you naturally do? Kind of speed back up a little bit, because you're like, okay, I don't have to stop after all. So I was slowing down because the speed limit was supposed to slow down, but I saw a red light in the distance. And then it turned green. And just out of habit, not really thinking, I sped back up. And I was going about 65. Right through that intersection. As I blew past the buildings, I thought to myself, something feels wrong. And then I saw a police car turn around and turn his lights. I'm like, I know something was wrong. And I got a very big ticket for that. And I wasn't trying to be bad. It's just, you know. So, big ticket. We're talking hundreds of dollars here. Yeah, that'd be a lesson to you. For shame. And a policeman's daughter, too. Can't believe you. Page 93. Page 93. I want you to do number 11 at your seats. Page 93, do number 11 at your seats. For what it's worth, I'm more careful when I go through Reynolds now. I pay close attention. When is their school secretary? They hit a cow at Smith Station, if I'm not mistaken. All right. Pause you where you're at, and we'll see if you're on the right track. Kendall, read it for us.
A driver in a moving car at 32 meters per second sees a cow sitting on the road 71 meters ahead. Can the driver stop in time to avoid hitting the cow if his rate of deceleration is negative 7.6 meters per second?
All right. I don't know if this is the Chick-fil-A cow or not. But they're always putting up directional signs, you know, chicken eaters this way or beef eaters that way, you know, right into the, that's one of my favorite signs is where they paint the overpass on the side of the brick wall, beef eaters that way. Anyway, so I'll write down my numbers. And what do I write down, Kendall?
Your initial velocity is 22 meters per second.
Okay.
Your displacement is 71 meters.
I hope not. Because if my displacement is 71 meters, I just hit the cow. The real question is, what is my displacement? And I hope it's less than 71, don't I? Yeah, let's hope it's not 71 meters. But it made it look like it, right? So I see why you said it, right? All right, the next thing.
The acceleration is negative 7.6 meters per second squared.
And then the last thing is, I've got to stop, right? Or the driver's got to stop. So therefore we know
The final velocity
the final velocity's got to be
is
0.
0.
Now this is the way I choose to do it. Technically, you could use the displacement of 71 and see what the final velocity comes to. And if it's 0 by then, or negative, which would mess with the math a little bit, but this is the best way to work it, is he's going to come to a stop from 32 meters per second at this deceleration rate. The question is, does the stoppage take more, less than, or equal to 71 meters? If it's equal to 71 meters, he bumps the cow and everyone's fine. If it's more than 71 meters, or would be more than 71 meters, he crashes into the cow and damages the car. And the cow just turns around and goes, moo, or eat more chicken, or whatever cows say. And then if it's less than 71, the cow just sits there and looks at him funny while he sits there and wonders what to do next. All right, so how many figured out that's the setup? What equation should we use here? What equation should we use, Audrey?
I use the dx squared
Good, and this is the equation we want, but we're going to solve it for the displacement. At your seats, finish this one out and then go on to number 12. Finish this one out and then go on to number 12.
No, go ahead.
How many found that yes, the driver stops in time? He can stop in about 67 meters, cow will be fine. He might wonder how to get around cow now, but cow survives. No animals were harmed in the writing of this problem. Questions on this one? Keep working on 12. Dude, remember to change the 8 kilometers into 8,000 meters. Do we get this acceleration 0.072 meters per second squared? Very slow acceleration, right? And that is already the 2 sig figs we wanted, or 7.2 e negative 2 meters per second squared. We go to find the time. Is there a way to find time without using acceleration? There is, if you'll find the average velocity first. And it's pretty easy to average 12 and 36 class. 24. So if you go just a little out of order, you could use average velocity as displacement per unit time, alternate these to get the displacement over the average velocity. And so we can take the 8,000 and divide that by 24. How much time does it take to get up to speed?
330 seconds.
Yeah, 333.3 repeating or rounded 2 sig figs, 330 seconds, or you could say, I suppose, what is that, 5.5 minutes? Though probably leaving 330 seconds is best. Now you could use the acceleration and these and find the time that way, right? Your acceleration equation, solve for time, VF minus VI over A. Again, that assumes that your A is accurate. I'd be honest, when I first saw that number, I'm like, I expected it to be low. I don't know that I expected it to be that low, so that's why I would shy away from it. But it should give you the same time, right? 36 minus 12, 24, and you divide 24 by 0.072, and you still get that same time. And of course, then you can finish with average velocity, it's just the 24. Questions on number 12? All right, no homework this evening. Just want to make sure you knew your exam is coming up on Tuesday. Exam's coming up Tuesday in this class. If you're watching on YouTube, that's lesson 42. Exam in lesson 42. All right, have a wonderful rest of your day, and you are dismissed.